Welcome back to Mechanical Design 1 course. Next week, we are proceeding to the next important topic, materials and process. Outline of this chapter will be as follow: materials and processes, material property definitions, tensile test, universal testing machine or UTM, stress, strain, modules of elasticity, elastic limit, yield strengths, ultimate tensile strengths, ductility and the brittleness, the compression test, the bending test, the torsion test, and ultimate shear strengths. So all of these are different type of mechanical property or definitions related to mechanical property of materials. Okay, so what do engineers mean when they talk about the stress? And have you ever experienced something breaking because of the stress you put on it? So we mean material, structure. So definition of a stress from the mechanical property point of view is something new to most of us. And we want to know what is the stress. Of course, we heard about human stress and human breaks under stress and tension, but we don't know what do we mean by stress in materials. So we will do some mechanical tests and we will come up with some mathematical formulation to understand the exact definition of stress in this lecture. Why do we study materials and process? So we need to understand material processes. To first, we need to select material, plus we need to calculate the life of a machine. We need to understand if that machine could endure those external forces or not, and how long that machine could work under that specific circumstances. A good machine design requires a true understanding of material properties, treatments, and manufacturing processes. This chapter, which is basically the chapter 2 of Norton book, presents brief metallurgical concepts and engineering material properties. So to get the material property, we have a variety of methods. But if we want to have two main category or to categorize it to main branches, we will have destructive and non-destructive tests. Destructive tests are used to determine the mechanical properties of materials under controlled loading conditions. So as it is clear from the name, we will destroy the specimen, we will destroy that sample to extract mechanical property. These controlled loading conditions in most cases may not duplicate actual load experienced by parts during machine operation. So we will extract mechanical property under specific laboratory conditions, but they may not fit exactly the environment of operation. So that's why we need to use safety factor and other statistical method. Variability in separate supplies of materials may also exhibit. So involves statistics in finding the right material property. The best material property data will be obtained from destructive or non-destructive testing under actual service loading of prototypes. And that prototypes should be your actual design made from actual materials from the actual material processes. Yes, so it's basically, if we do destructive tests, it's basically breaking the machine or part or structure on the real operating condition. And that could be expensive for some specific machines. Destructive test of actual material is usually done for the high-risk equipment such as aircrafts, submarines, automobiles, etc. So for example, for the aircraft wings, because it's very high risk, we want to be sure exactly what is a material property or mechanical property of that wing of aircraft. We need to put that under real or similar load condition of real um, operational environment and extract the mechanical property. Okay, so to extract the mechanical property, we could use different methods. And tensile test is the most commonly used test for material property measurements recommended by American Society for Testing and Materials, or ASTM. So the tensile test, which will be the topic of coming slides, will be, and it is, the most important test to extract mechanical property of materials. A universal testing machine, or UTM, is generally used to perform tensile tests. You will see what is UTM and how we could use UTM to extract mechanical property. The test specimen is threaded at both ends. So you could see here on the picture, you see here on the picture that the specimen, the test specimen is threaded. These are the threads at both ends, so it could be inserted into the UTM. The bar stretched slowly. So this is the bar, yes? The bar is stretched slowly in tension until it breaks, while the load and tensile across the gauge lengths are continuously monitored. So this is the gauge lengths, okay? So what do we monitor here? We monitor the distance across the gauge lengths and the bar. So the tensile test is basically force here outward. So if I could show here, um, so that will be the tensile test, tensile force. Okay, so that's the tensile force we apply by UTM to the threads of this specimen to increase the length of this specimen or bar. So this is UTM, and you could see here, these are jaws of this machine, and the UTM will keep the specimen tightly between these two jaws. Okay, so this is the specimen, and will apply the tensile force and will stretch the specimen until it breaks. And here you could see on this monitor, we could monitor the changes in the lengths and we could also monitor the force or the load applied by the UTM. Okay, we'll see a video of the tensile test, and we see how the load and how the lengths will change during the test, and we'll study the graphs in the coming slides. Okay, so parameters measured by UTM are load and deflection. Yes, so what is deflection? That length change, yes? But plotted as a stress and a strain. So we need to know what is a stress and what is a strain. So these two should be somehow be equivalent of load and deflection. They are not exactly load and deflection, we'll see, but they will be derived from load and deflection. So stress will be derived from load, strain will be derived from deflection. The result of a tensile test is in the form of a stress-strain plot. Stress is the load per unit area and is measured to be uniformly distributed across the cross section. So sigma is a stress. Sigma is the symbol we use across this book for the stress. So sigma represents a stress and is equal to the force, which is the tensile force, divided by cross-sectional area. So what is the unit of a stress? Unit of a stress is force divided by area, or Newton, divided by square meter, or Pascal. Or in American system is PSI, pound per square inch. Pound per square inch. Pound was unit of force, and inch was or is unit of length. So it's Pascal, yes, but I think you use Pascal for pressure before in physics, and pressure is basically opposite of tensile stress. So in tensile stress, we have these upward forces, but in pressure, we have these onward forces. Yes, so we have opposite forces in pressure. That's the difference between pressure and the tensile force or stress. But they have the same unit. We use Pascal for both of them. So here you could see we have our specimen. Okay. Here in this picture, we see free body diagram of two portion of this specimen. Yes. So if we virtually divide this specimen by 2 and we want to basically find a free body diagram of each of these portion, then we will see we have internal forces here, and that internal force should counterbalance the external force F. Here you could see we have two forces in opposite direction. So these two forces are actually action and reaction based on third law of Newton. But do we have really concentrated force at this cross section? No. This force is basically a resultant force, but it is not actual force. What's happening in the cross section we have contributed force. We have a contributed force of or stress of sigma. This is a contributed tensile stress, sigma. So sigma multiplied by cross-sectional area A will give us a resultant force of F. So here we have a very idealistic distribution of stress. In most cases, stress is not uniformly distributed in a real specimen. But since we are dealing with the engineering model, we need to make some assumption and do some simplification. So to do so, we assume that the stress will be uniformly distributed if we move far from the jaws of the UTM. Okay, so let's say at the middle of a specimen, we could assume that the force is distributed uniformly. Okay, but what is a strain? Yes, now we understood the definition of a stress, but we don't know the definition of strain. So we said that the strain is derivative of length change. So stress is the change in length per unit length. And across this book, we use epsilon to represent strain. So strain is represented by epsilon and is equal to the L minus L0. So L0 is initial length and L is the actual length. Yes, so when we apply the tensile force under that UTM machine, the length changes from the initial length to L. And L is more than L0 for the tensile test. And divided, so L minus L0 is the change in the length divided by the initial length, L0. The strain is unitless length divided by length. So here we could see we have this square which is infinitesimal square of the specimen. So let's say we have the specimen. I'm gonna draw it here. Okay. Okay, so let's say this is our specimen, and if I select infinitesimal cube or infinitesimal element of the specimen, that element is illustrated here. Okay, so this is our that small element here of the specimen, yes, and forces here is applied by the jaws of the machine, yes. So you see that this element changes to, so this solid element, the solid square is changing to this dash rectangular. And what is the stress applied to this element is sigma. Okay, So sigma stress is applied to this element, and that element is changing the length. So what is the change in the length is u, and the initial length was L. So initial length of this small element, infinitesimal element, is L, and the change of the length is U. So you see the nominal tensile test strain epsilon n is U divided by L. We have other type of strains. We have lateral strain as well. And that lateral strain is basically changes of the lateral lengths of these cube. The change of the lengths laterally is V divided by the initial length L will gives us lateral strain. But in tensile tests, we will monitor only the tensile strain. For now, we don't care about the lateral strain, but later we will use the lateral strain in coming chapters. And then we have definition of Poisson's ratio, or V. Poisson's ratio is equal to the minus lateral strain divided by tensile strain. Why do we have minus? Because we want to have a positive Poisson's ratio, and the lateral strain is negative for the tensile stress. Why negative? Because the V is negative, because the change of the length is negative, because L is less than L0 for the lateral side of this cube. So Poisson's ratio is another mechanical property of materials. For example, for steel, Poisson's ratio is about 0.25 to 0.3. So between 0.25 to 0.30 is Poisson's ratio of steel. And aluminum and other materials have different Poisson's ratio. So now you are familiar with another mechanical property. Okay, Hooke's law, we want to extract other mechanical properties similar to Poisson's ratio. Hooke's law, or E equal to sigma divided by epsilon, or stress divided by strain, equal to modulo of elasticity is Hooke's law. So E is the modulo of elasticity, or Young's module. E is a measure of the stiffness of the material in its elastic range and has units of stress. So let's see what we will see when we do the tensile test. What that UTM machine will plot for us. So here you could see for a ductile material, we have a stress strain plot of a tensile test. So what happens when we start to apply the tensile test? The length of the specimen increases. And if we release the force before we reach to that PLEL point, if we release the force, the material will spring back to the initial length. So material will act as just a normal spring. Okay, so here the slope of the line will be that module of elasticity, or that's why we call the slope of this line or module of elasticity or Young's module stiffness of the material. So similar to the stiffness constant of spring, K, this is basically the spring constant of the material or stiffness constant of the material, E. If we continue to apply load beyond that PL and EL, then we will move on to the plastic range. So here is the elastic range. Why? Because if we release the force before moving to the plastic range, the material will spring back to the initial length, and we will have exactly the same material as before. Nothing has changed, yes? The energy, the elastic energy, which is stored in inside the structure of the material, will be released. But if we continue applying the tensile force, then we will move on to the plastic range. It means that if we remove the force, the material won't back to the initial lengths. So if we just continue to apply force, finally we will reach to the fracture point or point F. At that point F, that specimen will break or will divide it by 2. Okay. Here we have another type of material, and as you could see, this one is low carbon steel, slightly different curve, but still the low carbon steel is type of ductile material. We will see what is the difference of ductile material and brittle material. But now, if I want to briefly explain you the main difference is that ductile material have huge range of plastic range, but brittle materials don't have the big plastic range, yes? So if they get out of this elastic range, they quickly fail and break. So they are more rigid. Brittle materials are more rigid. The tall material are more flexible. So here again, you could see the Young's module, and you could see the fracture point. We have other important points on this graph, and we want to know what are these points. Yes, we have yield strengths, we have ultimate tensile strengths, we have yield point, we have plastic point, we have elastic point, we have ultimate point, and we have fracture point. And we have two type of graphs here. We have engineering graph and we have true graph. What is engineering graph? Engineering graph follows the same mathematics we used in previous slides. For the stress, what was the stress? The stress was force, the tensile force, divided by A0. A0 was the initial cross-sectional area. But the cross-sectional area changes when we apply the tensile force. If you use that formula, F divided by A0, then we'll have that engineering graph. Why do we need that engineering graph? Because these engineering graphs are giving us a very good engineering model for further study, for further extraction of some mechanical properties like ultimate tensile strengths, and they are good enough for us. We don't need to make stuff complicated sometimes in engineering. We need just some assumption and simplification to extract mechanical properties. But what is the true graph? The true graph, instead of A0, will use A, or cross-sectional area, the real-time cross-sectional area. You see the huge difference happens between U and the fracture point because of the necking phenomena, because the cross-sectional area narrow down quickly when it reaches to the fraction. We'll see in coming slide what are those phenomena. Okay, so elastic limit, point beyond which the material will take permanent set, or elastic limit, or plastic deformation. So this is the EL, yes? Beyond that EL, we will take permanent set, yes? The permanent deformation of the material. Points PL and EL are often considered the same, yes? So the plastic and elastic points are often the same. They are slightly different in some specific material, but for engineering, for the sake of simplification and engineering modeling, we just consider the same. Yield strength. Yield strength is one of the very most important mechanical property that we could extract from the tensile test. Okay, at the point Y, here's the point Y. The point Y in most of ductile material are this, let's say, local maximum. At point Y, slight above elastic limit, the material begins to deform more readily, more easily. Why? Because you could see the stress value is almost the same, but the length is changing more quickly. The change of the length. The point is yield point, the Y point is yield point, and the value of stress is known as yield strength. So here is the yield strength. Offset of 0.2% is used for less ductile materials. So this is the less ductile material, that low carbon steel, sorry, this annealed high carbon steel, I'm sorry. So this is the basically less ductile material. We don't see that, let's say, the local maximum here. So how we could then extract the yield strength based on the standard definition, we just need to offset the strain here from the origin of 0.2%, then plot line parallel to the elastic line or elastic region, and the cross point of this, let's say, auxiliary line, and the real curve will give us point Y and yield strengths. So again, so far, you should be familiar with Young's module. It's one of mechanical property we managed to extract from that tensile stress. The other one is yield strength. The stress in the specimen continues to increase. Okay, so this is the stress, yes? So we are on that ultimate tensile stress test. So if you go beyond the elastic point and move to the plastic point, the stress in the specimen continues to increase non-linearly. You see, this is the part, this part is non-linear to a peak or ultimate tensile strength value SUT at point Y. Sorry, at point U. So here, point U, you have the tensile strength SUT. This is considered to be the largest tensile stress the material can sustain before breaking. So this is the largest tensile test. Of course, again, engineering stress, yes, not the true stress. This is the largest tensile stress that could be sustained before breaking. SUT. SUT or ultimate tensile strength is again one of important mechanical properties that we could extract from this tensile test. However, for the ductile steel curve shown, the stress appears to fall off to a smaller value at fracture point F. The drop in apparent stress before the fracture point is an artifact caused by necking down or reduction in area of the ductile specimen. So here you could see the fail part under this UTM machine, and you see the necking. You see that the cross-sectional area change here. Here you see the necking phenomenon. Yes, so this cross-sectional area now is less than the initial cross-sectional area we had in the specimen. Okay, so we are done with that ultimate tensile strength definition. We have another mechanical property which has less important, but this is used and is very important for material selection and working with the selection material graphs. So specific strength is the strength divided by density. So now we are familiar with two types of strengths, yes? Yield strength and ultimate tensile strength. If we divide them, if we divide each of these by density of the material, then we will have specific strengths. We'll have specific yield strengths, we'll have specific ultimate tensile strengths. And is important in developing lightweight machines. So for example, for aircraft, if you want to have strengths, but at the same time, you want to have a less weight, you want to have a lighter structure. Ductility and brittleness. Tendency of material to deform significantly before fracture is measure of its ductility. So when they have large plastic region, it means that we have higher ductility and the material is ductile. If you have very small plastic region, it means that the material is less ductile or is brittle. The ductility of material is measured by its percent elongation to fracture or percent reduction in area at fracture. Okay, so here we have a brittle material. Cast iron is a brittle material. They have high carbon, and the high carbon content will make the iron more brittle. So you see that we don't see that necking phenomena that we used to see in steel, in more ductile materials. Yes, and that's why that ductility or brittleness could be measured by percent reduction in area at fracture. Materials with more than 5% elongation at fracture are considered ductile. So here you see we have only 0.2% elongation. And this material, this stress strain graph of a tensile test of a material shows clearly that we have a brittle material. Why? Because we don't have that large basically the large plastic region that we used to have in ductile material. Okay, so when we have more than 5% elongation, so this one is 0.2%, so 5% will be almost this. Yes, almost this. Then basically we could consider the material as ductile. Manufacturing methods and heat treatments may also affect the ductility of material. We'll explain them later, why a manufacturing method and heat treatment could change ductility or brittleness of material, yes? But anyway, if you put that specimen under the UTM machine and extract that stress strain, we will see a much less plasticity region. So we could call it brittle, yes? Brittle materials don't have a clearly defined yield point and plastic region. So here we have our ductile material, yes? This ductile material don't have a very clear yield point. How could we extract the yield point? We'll use or follow the same standard we use for that anneal cast iron. So if we offset from the plastic line by 0.2% and use that auxiliary line parallel to the plastic line, the intersection of this auxiliary line and the curve will give us the yield strengths. What about the ultimate tensile strengths? Of course, we cannot see the ultimate point, so ultimate tensile strengths for brittle material will be exactly same as the stress at the fracture point. Okay, let's watch a tensile test.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper cross head into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luders strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength RM. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 mm, the result is 0.2 mm. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 mm of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. The 0.2% proof strength, Rp 0.2, is equal to Fp 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture, and percentage reduction of area are calculated in the same way as in the first test.
Okay, so in this video, they use different notations for, let's say, yield strengths or ultimate tensile strengths, but the concepts are almost the same. Definitions mathematically are the same.